Hey guys, my name is IBM and I am solving 9702 paper 22. This is Feb March 2024 papers. This is AS level structured equations, February March. So the question paper is attached in the video description. You can always download and follow through the videos. Without wasting time, I'd like to take you to the question paper. So this is the question paper of Feb March. Many students have been asking for this, so I will not hesitate to record it. So the paper is 1 hour and 15 minutes. I'm going to try my level best to keep time. So without wasting time, I'll not go through the instructions. I'll just go straight to the question number 1. The table 1.1 lists some SI-based quantities. Complete the table by indicating with a tick which rows are SI-based quantities. Remember, SI-based quantities are 7. We have mass, we have length, we have time, we have temperature, we have current, we have luminous intensity, and we have amount of substance. Those are the base quantities. So just check through here. We have current. Energy is not a base quantity. Force is not a base quantity. Then we have mass. Mass, length, time. That is mass, length, time, temperature, current, luminous intensity, amount of substance. Those are the 7 base quantities. So energy and force are not base quantities. Use the definition of power to determine its SI base units. So first of all, we write the definition of power. Power is equal to the work done divided by the time taken. That is the power. So that means this is going to be the force times distance, that is work done, then divide by the time t. So the units for power will be force, which is kilogram meters per second squared, because force is mass times acceleration, then times distance over t. The mass is kilograms, acceleration is meters per second squared, and d is in meters. Then divide this by time, which is in seconds. So this simplifies to kilogram meters times meters. So there is a meter here. It is kilogram meters per second squared, then times meters. So it becomes kilogram meters squared. Then s power minus 2 divided by s power 1, it becomes s power minus 3. So it means the units here are going to be kilograms meters squared times s power minus 3. A light meter is used to measure the intensity of the light in a classroom. The light is incident normally on the sense of the meter. The sensor has an area of 2.2 centimeters squared. The reading on the meter is 950 watts per meter squared. Capture the power of the daylight incident on the sensor. So we know that intensity is equal to the power per unit area. So it means the power is going to be the intensity times the area. So they have given us the reading. The intensity is this one, watts per meter squared, and they have given us the area. So I'll just multiply this. So this is going to be 950 times the area, which should be 2.2. I have to change this to meters per second, meters squared, so it is 10 to the power minus 4. So this is 2.2 times 10 to the power of minus 4. So I'll check with the calculator. 950 times 2.2 exponent minus 4. So this is giving me 0.209. So the power is going to be 0.209. So that is question number 1. Question number 2. So you can write this to two significant figures, 0.21 watts, but I want to encourage you to avoid writing answers to less than two significant figures. The smallest should be two significant figures unless otherwise, or unless the answer is exact. Then define acceleration. Of course, we know that acceleration is change in velocity over time. So we can define acceleration as the rate of change, of velocity. Now in the previous marking, the rate of change of velocity, in the previous marking, if a student says rate of change of velocity per unit time, this is a contradiction. It's like defining rate of change of rate, So you must define it as rate of change of velocity or change in velocity over time, but not rate of change of velocity per unit time. That is a repetition. So it's just a matter of saying rate of change of velocity. An Olympic diver stands on a platform above a pool of water as shown in the figure. Okay, so we notice that the velocity has two components. One in the horizontal would be 5.9 cos of 60. If I consider the velocity in the vertical, it would be 5.9 sine of 60. Okay, so when the diver is on the platform, his center of gravity is vertical height 9 meters above the surface of the water. The diver jumps from the platform with a velocity 5.9 at an angle of 60 degrees to the horizontal. Air resistance is negligible, so it means we shall use G as 9.81 meters per second squared, because if air resistance is negative and if G is constant, then the equations of motion can work here. When the diver hits the surface of the water, his center of gravity is a vertical height of 1.2 meters above the surface. Remember, it was initially 9 point, so its center of gravity has changed through this vertical distance here. So which is 9.2 9.0 minus 1.2. So it means his center of gravity has moved through a vertical distance of that is, I think that is 7.8 meters. Capture the speed of the diver at the instant when he hits the velocity of the water. So first of all, there are two ways of solving this. You can use energy conservations. For instance, as he's diving, he's losing gravitational potential energy as he gains kinetic energy. So I can use that simpler method first. I'll use two methods maybe. So I'll say the loss in gravitational potential energy is equal to the gain in kinetic energy. So the loss in gravitational potential energy is mg change in height, and the gain in kinetic energy is a half m v squared. So m cancels out. I want a v, so I'll say v is going to be twice times g times change in height, and this will be under the square root. So this will be the root of 2 times 9.81, but the change in height, in the vertical height, is going to be, remember it was 9.0 minus 1.2. So I'll just check with my calculator. So this is 2 times 9.81. 2 times 9.81, then times, this is 7 point 7.8 under the square root. I don't think this is going to be working. Let me look here. How does the diver dive? When the diver hits the surface, when the diver is on the platform, his center of gravity, okay, the diver jumps from the platform with a velocity of 5 point. Okay, so he had some speed. So there's something I've messed up here. He had a speed of 5.9 at the platform, and we want the speed at this point. So here it is going to be changed in v squared, not because that is the gain in kinetic energy. So this should be the change in v squared. So this is not going to be correct. So I'll say, since of course the mass cancels out, so I'll have that g change in height is equal to a half. Let's say v2 squared minus v1 squared, where v1 is at the platform. So I'm trying to find v2 because this is going to be the gain in kinetic energy. So I'll say this is going to be 2 times 9.81 times the change in height, which was 9 minus 1.2. This is going to be equal to v squared, v2 squared minus v1 squared, which was 5.9 squared. Okay, so it means v2 squared is going to be equal to 5.9 squared plus 2 times 9.81 times 7.8. I made v2 squared the subject. So I'm going to find the square root on both sides. Okay. So this is going to be 5.9 squared plus 2 times 9.81 times 7.8. Then I find the square root of the answer. So it means v is going to be 13.7. So the answer here is going to be 13.7. Okay, I want to use a simpler method of resolving. Of course, if we consider motion, equations of motion, velocity in the horizontal does not change, remains the same. So I'll say velocity in the horizontal is going to remain the same, which is 5.9 cos of 60. That is velocity in the horizontal. What is 5.9 cos 60? 5.9 cos of 60. So in the horizontal, the velocity is 2.95 meters per second. The velocity in the horizontal remains constant because there is no force, resultant force in the horizontal. The only force acting is the force due to gravity, which acts in the vertical. Then in the vertical, if I try to find velocity in the vertical, I'll go to VV or V subscript V. I'll say V subscript V squared is equal to initial velocity in the vertical squared plus 2 times acceleration in the vertical times S in the vertical. So I'm using V squared is equal to U squared plus 2AS. So V in the vertical, which I'm going to call V subscript V, is going to be equal to the square root of initial velocity in the vertical. We resolve 5.9 in the vertical, which gives us 5.9 sine of 60, but this should be squared. Then plus, if it jumps slightly above the point of projection, it means this is going to be negative. This becomes minus because g is going to be a negative. So this will be minus 2 times 9.81. Of course, the vertical distance remains the same, times 70. It was 7.8. Okay, so we can press our calculator here. 5.9 sine of 60, but this should be squared. Then minus 2 times 9.81 times 7.9. Oh yeah, this should be, because if I consider displacement, the displacement is below the point of projection. This will be minus 7.8 because the resultant displacement is 7.8 below the point of projection over the point through from which it fell. So here the displacement, the sign of the displacement will be negative. So negative minus for g, and then this minus, it makes it a positive. So I'll just multiply this by -1. Then I find the square root So here it is giving me velocity in the vertical as 11.2. Let me repeat again, 5.9 sine of 60 squared. So this will be plus, not minus, plus 2 times 9.81 times 7.8. Okay, then root of the answer, that is 13.4. So I'll write here 13.4 meters per second. Note that this minus is because g is a negative since it moves at an angle above the horizontal. Then this negative here is because the displacement was below the point of projection, so the displacement is negative. So then we find the resultant velocity from Pythagoras theorem. We have a velocity in the vertical downwards and velocity in the horizontal. Then we need the resultant. So that is going to be the square root of 2.95 squared plus 13.4 squared. So 13.4 squared plus 2.95 squared under the square root. So this is giving me exactly 13.7 meters per second. Then the diver in B enters the water and it decelerates. Decelerates meaning that it slows down. It slows down. So that means the speed decreases. And of course, if the speed decreases, the drag force also decreases. Remember, the frictional force is always directly proportional to the square of the speed. So if the speed decreases, the drag force decreases. Describe and explain the variation of the viscous drag force acting on the diver in the water as he moves downwards. The viscous drag depends on the speed. It's like air resistance. It depends on the speed. So as the diver moves down, the speed decreases because they say it decelerates. So the viscous force or viscous drag decreases. So as the diver moves down, their speed decreases because they said decelerates, so their speed decreases. So the viscous drag force also decreases. So viscous drag force is like friction. If the speed decreases, the friction decreases. Or if the speed in a medium or in a fluid decreases, the resistive force from that medium also decreases. So this one decreases. Then the diver has a volume of 7.5 times 10 to the power of minus 2 meters cubed. The density of the water is 1.0 times 10 to the power of 3 kilograms per meters cubed. Show that the upthrust acting on the diver when he is entirely underwater is 740. So we know that upthrust is equal to the weight of the fluid displaced according to Archimedes' principle. So this is going to be mg, which is going to be the density of the fluid times the volume, then times g. Of course, the volume of the diver is the same as the volume of the water he displaces. So this is going to be the density, which is 1 times 10 to the power of 3, times the volume, which is 7.5, times 10 to the power of minus 2, then times g, which is 9.81. Okay, so I just press my calculator. 1 exponent 3 times 7.5 exponent minus 2, then times 9.81. So this is giving me 735.75. 735.75, which is approximately 740 newtons to two significant figures. At a particular instant when the diver is entirely underwater, his horizontal velocity is 0. His horizontal velocity is 0. The viscous drag force acting on him at this instant is 950 newtons, acting vertically upwards. The diver has mass of 78 kilograms. Determine the magnitude and direction of the acceleration of the diver. So let's assume this is the diver. His weight mg is acting vertically downwards. The drag force upwards is given as 950 newtons. Of course, the upthrust also acts upwards. The upthrust is 740. Determine the magnitude and direction of the acceleration of the diver. First of all, the resultant force is upwards. So the resultant force is going to be the forces upwards, which is the drag force. The drag force always, of course, acts in the opposite direction to motion, is moving downwards. So the drag force is upwards. The upthrust for it is always upwards, whether you're moving up or down. So that is the total force upwards minus the total force downwards, which is the weight, which is mg, which mg is going to be 78 times 9.81. That is the resultant force. But remember, the resultant force is equal to mass times acceleration. So the acceleration is going to be, I think this is, what is this? 950 plus 740 minus 78 times 9.81. So this is 925, approximately 925. So I'll say A is equal to 925, that is the resultant force, divided by the mass, which is 78. So 925 divided by 78. So that is 11.2, I mean 0.9. So the acceleration is going to be 11.9 meters per second. And because the resultant force here is upwards, so it means the acceleration is vertically upwards. So this is vertically upwards. The acceleration is always in the same direction as the resultant force. So because total forces upwards are bigger than the force downwards, then the resultant force is vertically upwards. Question 3. A thin metal wire X of diameter 1.2 times 10 to the power of minus 3 is used to suspend a model planet as shown in the figure. The variation with the strain of the stress for a wire X is shown in the figure. Okay. The strain in X is 5.4 times 10 to the power of minus 3. Remember, strain is given as so use figure 3.2 to calculate the force exerted on the wire by the model planet. So I know from stress equals to force, stress equals to force over cross-sectional area. So it means the force is going to be the stress times the area. And remember that area is going to be pi r squared. Because it is a sphere, it is a model planet. And what is given here is a cross-section. They gave us the diameter. It is a thin metal wire, so it is a circular, it is not a sphere, it's not spherical, so it is pi r squared. So I'll just substitute here to find the force. The stress is, I'll check this 5.4 times 10 to the power of minus 3, 5.4. So the scale here is 0.2, 1, 2, 3, 4, 5, that is 5. This is 5.2, 5.4 is here. The corresponding stress is, the scale on the vertical is 0.02. So 1, 2, 3, 4, 5, 6. I will say 6 times 0.02. 6 times 0.02, then I add this to 0.6. So this is 0.72. Okay. So the corresponding stress is 0.72. Then the power of 10 is gigapascals. So I'll say times 10 to the power of 9 times 10 to the power of 9, then times the area, which is going to be pi, times the radius. Did they give us the radius? They gave us the diameter, so the radius is going to be 0.6 times 10 to the power of minus 3 meters. So I'll just say times 0.6 times 10 to the power of minus 3, and this is squared. I just divide the diameter by 2. So 0.72 exponent 9 times pi times 0.6 exponent minus 3, but this is squared. So this is giving me 814. So this is 814 newtons. 814 newtons. If you want, you can write 810 newtons to two significant figures. The elastic potential energy of X is 0.31 joules. Capture the original length of the wire before the model plant was attached. So we know that elastic potential energy is equal to a half times F times X, where X is going to be the extension, which means X is going to be twice elastic potential energy divided by F. So this is going to be 2 times the energy, which is 0.31 divided by the F. The force I've got is 8. I'll use 814 newtons. So this is going to be 2 times 0.31 divided by 814. So this is giving me X as 7.6 times 10 to the power of 1, 2, 3, 4. 7.6 times 10 to the power of minus 4. 7.6 times 10 to the power of minus 4. You could have used 810, or you could have 2 times 0.31 over 810, which could give you a slightly different answer, but the tolerance will depend on the examiner. So you expect to get either 7.6 or 7.7, depending on how you round it off meters. Okay, you can use another method. Here I choose the simplest. Wire X is replaced by a new wire Y with the same original length and diameter, but double the Young modulus. Okay, remember this is a graph of stress against strain. It is a graph of stress against strain. So we know that Young modulus is equal to stress divided by strain. So if it is a graph of stress against strain, it means stress is equal to Young modulus times strain, which means Young modulus is equal to the gradient. So they say the other wire has twice the gradient. Has twice the Young modulus, and Young modulus is equal to the gradient. So it means the gradient of the new wire is going to be twice, is 2 times. So it is 2 times this line here. So I'm going to try and estimate the gradient of this one. Or alternatively, since it is also going to go through the origin, I just want to make sure the gradient is twice. So I'm going to look for simpler points to choose for the gradient. For example, if the gradient of this first line, if I'm using this point here, if that is 0.8 divided by 6 is the gradient, then this is going to be equal to, I'm using a simpler method to find the new gradient. So this is 0.8 divided by 6. So this is 2 over 15. The gradient of that is 2 over 15. The gradient of the new wire new gradient is going to be 2 times 2 over 15, which is going to be 4 divided by 15. So I'm going to choose a simpler point to find if, let's say the strain is, I'm going to use 4. If the strain equals to 4, what is the strain? What will be the stress? The stress is not known, but the gradient should be 4 over that. So I'll say the unknown stress divided by 4 should give us 4 over 15. So it means the stress is going to be 4 times 4, which is 16 over 15. So I'm looking for a corresponding point to see if I can put on the graph. So 16 divided by 15. That is 1.06. Let me check. It is too big. I can't have it on the graph. I'm going to choose another point. Let me use 2. Let me check 2. If the strain is 2, I'm changing this to 2. If the strain is 2, so this will be 2 times 4, which is 8. So I'm going to check 8 divided by 15. 8 divided by 15, 0.53. 0.53. Let me check 3. I want a point which is easy to use. Let me check 3. If it is 3, this will be 12. I'm looking for a simpler point to plot so that the gradient is twice. I've decided to use a simpler mathematical method. So this is 4 times 3, which is 12. So let's say 12 divided by 15, that is 0.8. Okay, so it means when the strain is 2, the stress is 0.8. So my line is going to go through that point. So I'm just going to draw a line here. As long as it goes through that point, the rest is history. Okay, so this line is having a gradient, which I think is twice. It's having a gradient which I think is twice. The other one we can check. 0.8 divided by 4, divided by 2. 0.8 divided by 2 is 0.4. No, it is supposed to be 3. Sorry about this. This is supposed to pass through 3. I used the 3, not 2. Because I chose strain as 3, so it is here. Sorry about that. Let me increase the thickness. Okay, so that would be the new line. I chose the gradient should be twice, first of all. So the new gradient is the first gradient times 2. I go the first gradient as 2 over 15. So the new gradient is 4 over 15. Then I chose a pair of points. So I said when strain is 3, what is the stress? So I got the stress as 12 over 15, which is 0.8. I plotted that point. Of course, the line should go through the origin. So that is going to be the line. Sorry for the delay. Then question number 4. Of course, question number 4 is very easy. Nucleus P undergoes alpha decay. We know that alpha is 4,2. So if we try to balance the proton number, this is 84 minus 2, which makes this to be 82. 215 minus 4, which makes this one to be 211. State the principle of conservation of momentum. Of course, we know that for conservation of momentum, the total momentum of an isolated system of interacting bodies is always constant. Total momentum total momentum of an isolated system of interacting bodies is always constant. Avoid stating this principle by saying is conserved, not at all. When I talk about isolated system, it is the same as closed system. It is a system for which there is no resultant force acting. It's a system for which the sum of the sum of total of momentum before collision is equal to the sum of momentum after collision, provided no resultant force is acting. So it's as easy as saying the total momentum of an isolated system of interacting bodies. This should not be stated for one body, it should be bodies. This should be plural. Is always constant, don't say conserved. Before the decay, nucleus P has a speed of 3.2 times 10 to the power of 5 meters per second. After the decay, nucleus Q is stationary. So that means its momentum is 0. Calculate the speed of the alpha particle after the decay. So total momentum before collision should be equal to total momentum after the collision. So it means total momentum, I will say momentum, I'll use P for momentum. Total momentum of P should be equal to momentum of the alpha particle plus the momentum of Q. That is by conservation of momentum. Remember, momentum is mass times velocity. So total momentum of P before the collision is going to be its mass. What is P? The mass of P is going to, because these are nuclei, the mass of P is going to be 215 times U, where U is the unified atomic mass. Then times, that is mass, times the velocity, which is 3.2 times 10 to the power of 5, should be equal to, because they say the Q is stationary, so that will be 0. So this should be equal to momentum of the alpha particle, where its mass is going to be m, 4u, then times its speed, which we don't know, I'll call it v, then plus the momentum of Q, which is 0. Okay, so that is total momentum after the collision. So we need to find V. Of course, U is going to cancel out because it's both on both sides. So it means V is going to be 215 times 3.2 times 10 to the power of 5, and then I divide this by 4. 215 times 3.2 exponent 5, then divide this by 4. So this is 1.72 times 10 to the power of 367. So 1.72 times 10 to the power of 7. Then question number 5. By reference to the direction of propagation of energy, state what is meant by a transverse wave. Of course, for a transverse wave, we know that the particles vibrate perpendicular to the direction of propagation of energy. So this one, particles vibrate perpendicular to the direction of propagation of energy. That is a transverse wave. Remember, for longitudinal, it would be particles vibrating parallel. Do not forget to mention particles vibrating perpendicular to the direction of propagation of the energy. Next time it will be longitudinal. For longitudinal, particles vibrate parallel to the direction of propagation of energy. Then a space telescope is designed to detect electromagnetic radiation with wavelength in the range 12 times. So this is going to be 12 times 10 to the power of minus 6 to 28 times 10 to the power of minus minus 6. When I convert this, it is the same as 1.2 times 10 to the power of minus 5 up to 2.8 times 10 to the power of minus 5 meters. Of course, this is automatically infrared, remember. Reed's mother is visiting Uncle Xavier's garden. And for visible, we have 10 to the power of minus 7 meters. On the left, we have a higher wavelength. So next is going to be 10 to the power of minus 2, 10 to the power of minus 3, 10 to the power of minus 1 up to 10 to the power of 4. So this is going to be infrared. Automatically, this is going to be infrared. Because the wavelength is of order 10 to the power of minus 5. That is on the left-hand side of visible light, where visible light is 10 to the power of minus 7. So this is infrared. A detector on another space telescope detects an electromagnetic wave. The signal from the detector is transmitted to the Earth and displayed on an oscilloscope as shown in the figure. The frequency of the signal displayed on the oscilloscope is equal to the frequency of the detected electromagnetic wave. Okay, so it means we can find the frequency because the detected electromagnetic wave has wavelengths in the range 12 power minus 12 micrometers to 28 micrometers. The time-based setting on the oscilloscope is 5 times 10 to the power of minus 15 seconds. Capture the wavelength of the detected electromagnetic wave. So we have the time-based setting. My students always prefer to use X for time-based setting. So let's see on the X-axis, we have 1, 2, 3, 4, 5, 6. This is one cycle. So the length is 6 centimeters. So the period is equal to the length of one cycle times X, which is going to be 6 centimeters times 5.0 times 10 to the power of minus 15 seconds per centimeter. That is the period. Then, to find wavelength, we know that speed c is equal to lambda times f. C is equal to lambda over t because f is 1 over t. So the period, the wavelength lambda is going to be equal to c times t. So this is going to be c, which is the speed of light, 3 times, because this is electromagnetic, so it is 3 times 10 to the power of 8 times the period, which is 6 times, of course, per centimeter cancels with that. So it is 6 times 5 times 10 to the power of minus 15. So we have 3 exponent 8 times 6 times 5 exponent minus 15. So this is giving us 9.0 times 10 to the power of minus 6 meters. Question number 6. Coherent visible light of single frequency is instant normal on a double slit. It is a double slit. Remember, for a double slit, lambda is equal to AX divided by D. This produces a pattern of bright and dark interference fringes on a screen as illustrated in the figure. There are 7 bright fringes. Now they have given us the distance. This is X, 2X, 3X, 4X, 5X, 6X. So 6 times the separation of bright fringes is equal to 10.2, which means the distance between two successive bright fringes is 10.2 millimeters divided by 6. This is millimeters. Okay. Explain how the pattern of bright and dark interference fringes are formed. Of course, we are explaining how interference fringes are formed on the screen. So first of all, light waves must undergo diffraction from the slits. They should meet at the screen. When they meet, either constructive interference occurs when the path difference is 0, or destructive interference will occur when the path difference is 180 degrees. When the path difference is wavelength, or the phase difference is 0 degrees. So I'll explain in terms of phase difference. So one, I would say light waves diffract, or you can use the word spread. I have to reduce the thickness, it's looking so weird. Light waves diffract or spread at the slits. Of course, they diffract at the slits. Then the diffracted light from the slits or from each slit superpose at the screen or meet at the screen. Superpose at the screen. Superpose at the screen. So if the waves meet with a phase difference of 0, a bright fringe or intensity maximum is formed. When the phase difference, you could mention path difference. Of course, phase difference is 0. Path difference is also 0 for maximum. Then phase difference is 180. Path difference is lambda over 2 for intensity minimum. So when the phase difference is 0 degrees, can I say only 0 degrees? Okay, 0 degrees, 360. When the phase difference is 0 degrees, a bright fringe or intensity maximum is formed. And when the phase difference is 180 degrees, then of course that means a darker fringe or an intensity minimum is formed. A dark fringe, or call it intensity minimum, is formed. Now, instead of saying phase difference is 0 degrees, you could mention the general equation, which is n times 360. But of course, here it means you have to mention n equals to 0, 1, 2, and so on and so forth. Path difference in a similar way, and so on and so forth. You could here I just stated only one condition for phase difference of 0 degrees Celsius, but could be 0, 360. You go on adding one cycle. Here it is 180 plus you go on adding one cycle on 180, and so on and so forth. So when the phase difference is 180 degrees, a dark fringe or intensity minimum is formed. So this gives me, at least I can get the 3 marks. When you just mention they diffract and meet without specifying the conditions for constructive interference and destructive interference, then you would get 1 mark. When the path difference is 0 degrees Celsius, when the path difference is 0 degrees, a bright fringe or intensity maximum is formed. The reason is very simple. A constructive interference occurs. Constructive interference occurs. So here, for the second one, phase difference is 180 degrees. Destructive interference occurs. So that's why we have those maximum for 0 degrees Celsius and minimum for 180 degrees. The distance between the centers of the bright fringe X and the bright fringe Y is 10.2 millimeters. The slit separation, remember the slit separation is A. The distance from the slits to the screen is 3.1, this is D, actually the wavelength. So we know that lambda is equal to AX divided by D. So A is 1.2 times 10 to the power of minus 3. X is the slit separation. Remember we said X was 10.2 divided by 6. So X was 10.2 divided by 6, but we have to change this to millimeters, to meters, so it is times 10 to the power of minus 3. And this is going to be, okay, this was in millimeters. Then I have to divide this by D, which is 3.1. So 1.2 exponent minus 3 times 10.2 exponent minus 3. I first divide this by 6, then I divide by 3.1. So this is giving me 6.6 times 10 to the power of minus 7. 6.6 times 10 to the power of minus 7. The light is replaced by a different visible light with a shorter wavelength. Remember, lambda is equal to AX divided by D. Now it is a shorter wavelength. Lambda has decreased. Set how the new fringe separation will compare to the original separation. D is not changing. Lambda is not, the slit separation is not changing. We are comparing lambda with the fringe spacing. So since lambda decreases, X also decreases. So I can say lambda is directly proportional to X. So the new fringe separation will be smaller. So the new fringe separation will be smaller. Okay, or it will be less, or it is reduced. Because lambda decreases, X also decreases. Because lambda decreases, X decreases because they are directly proportional. A stationary wave is formed on a stretched string AB as shown in the figure. P, Q, and R are points on the string. On the figure left, draw a cross to show the position of a node. Because this is a stationary wave, I could complete this by drawing a loops to just fill up this. So it means the node is going to be here, or it is this point here, or this point here. Draw a cross to show the position of a node. So I have so many points to draw that cross. You could draw it at A, you could draw it at that point, you could draw it here, you could draw it there. That is where the node is. Instead, the phase difference between P and Q, of course, particles in the same segment, P and Q are in the same segment, because if I was to complete this, remember, P and Q are in the same segment, particles in the same segment vibrates in phase, so this is 0 degrees. Then state the phase difference between P and R. P and R are in two adjacent segments. Particles in two adjacent segments vibrate 180 degrees out of phase. So this is 180. There's no calculation here. You must have mentioned this in your class. Next is electricity. Define PD. Of course, we know V is E over Q. So that is energy transferred from electrical to thermal per unit charge. Energy transferred. Energy transferred from electrical to thermal per unit charge. Energy transferred from electrical to thermal per unit charge, that is PD. A cell of EMF 1.8 volts and internal resistance R is connected in power with a resistor of resistance 6 ohms and a filament lamp as shown. The switch S is open. So S is open. The ammeter reading is 0.25 amperes. when S is open. So that means we can tell the PD across 6 ohms. Okay, determine the internal resistance of the cell. Okay, so we know that EMF is equal to the terminal PD plus the lost volts. So the EMF E is equal to terminal PD, which is the current times the fixed resistor or the external resistor plus the current times the internal resistor. So I times R is going to be equal to the EMF, which is 1.8. The EMF is 1.8 minus I times capital R. Remember, I is 0.25 is equal to 1.8 minus 0.25 times 6. Remember, the current, if the switch is open, the current in here is the same current through here, which is 0.25 amperes. So I will just, there's a small r here. So it means small r is going to be 1.8 minus, what is 0.25 times 6? That is 1.5. So this is 1.5. Then I divide this by 0.25. So 1.8 minus the answer divided by 0.25. So this is giving me 1.2. So this is 1.2 ohms. You can use any other method, but to me this is the easiest. Alternatively, we would find the total resistance, but it's almost the same thing because EMF is equal to current times total resistance, which will give you the same thing. Then at T1, switch S in figure 7.1 is closed. Figure 7.2 shows the variation with the time T of the ammeter reading I. State whether the EMF of the cell after T1 is greater than, less than, or the same as it was before T1. Of course, EMF is the total energy available in a circuit, and the total energy depends on the properties of the battery. So the EMF does not, it can't go, the EMF is a constant, so this remains the same. It is the PD which changes, but the EMF is the same, or it is not changed. The EMF is a constant. Because the EMF is total energy available in the circuit, which is coming from the cell. So we don't expect it to be greater. It can't be less. If it is less, then it is we are talking about the terminal PD. By considering the effect of the lamp on the total resistance of the circuit, explain the variation of the ammeter reading shown in figure 7.2. So let's look at first. The current is constant. That means the resistance is constant because V is equal to IR. So the current is constant, resistance is constant. Then the current increases. Here I increases, which means resistance decreases because they're inversely proportional. They're inversely proportional. Then here we see that the current now decreases, which means the resistance increases. But what might have happened to the lamp here? Maybe the temperature increased for the filament lamp. Okay, so I'll just put this in writing, which is very easy. If you have been in class, that part of the filament lamp is very easy. So I will say before T1, the current is constant because they were saying explain the variation of the ammeter reading. The current is constant because total resistance is constant. Initial total resistance is constant. Then at T1, exact at T1, we see that the current increases rapidly. So current increases. Why does current increase? Because total resistance decreases. Total resistance decreases. Why does total resistance decrease? They said at time t1, switch S in the figure is closed. So we have to, because we are going to be having this resistor here and this one in parallel. So total resistance in the parallel decreases. So total resistance first decreases. Total resistance decreases due to decrease of the external resistance. In bracket, I'm saying we have resistors in what? In parallel. We have resistors in parallel. One for the fixed resistor and one is the resistance of the lamp. Then in parallel, total resistance in parallel is less. Then after T1, we see again the current is decreasing. So we are saying after T1, maybe the temperature of the lamp increases. So the resistance of the lamp increases. What is the effect? Total resistance. So total resistance increases, hence the current in the ammeter decreases. Remember, for a filament lamp, with the time, its temperature increases. And remember, if temperature increases, the resistance of the filament lamp also increases, which means total resistance is higher, so the current should be lower because current is inversely proportional to resistance. Okay, and lastly, I think particle physics is the simplest topic, which my students always get everything in particle physics. These are just simple facts. State the name of the class or group of fundamental particles that contain a neutrino. Of course, a neutrino, an electron, antineutrino, these fall in what we call leptons. These are leptons. And leptons are fundamental particles. A hadron P has a charge of positive 1e, where E is the elementary charge. The hadron P is composed of a down antiquark and only one other quark. The hadron has a down antiquark and only one other quark. Of course, the other quark cannot be, because it's a hadron which is made up of a quark and an antiquark. This is most likely going to be a meson. So identify the possible flavor for this other quark. Of course, the type of the hadron is automatically meson. It is a meson which has an antiquark and a quark. So the charge should be positive 1e. So the other quark, because the anti-down has a charge of 1 over 3e. So 1 over 3e plus q should give us positive 1e. So what is q? So q is going to be 1e minus 1 over 3e, which is the same as 2 over 3e. And this is going to be either top, charm, or up. So this is going to be an up quark, because the charge of the other quark is 2 over 3e. It is up, or it can be charm, or it can be top. You just choose one of these, an up quark, a charm, or a top quark. You don't mention all of these. The nucleus Q undergoes radioactive decay to form nucleus R, emitting an antineutrino. So an antineutrino has no mass, no charge. And another particle X. Of course, an antineutrino must be accompanied by a particle which is going to be a normal particle. So this is going to be beta minus, or E 0, -1, 0, -1. So state what particle is represented by X. So X is going to be beta minus. It is beta minus particle, or you can call it the electron. Whenever somebody just mentions the electron, is referring to beta minus. It is an electron which is accompanied by an antineutrino. If it was a neutrino, this would be a positron, or beta plus. Then compare the nucleon number of Q and R. Nucleon number. So if this is A and Z, this is going to be A. The nucleon number of Q and R is going to be the same. So this is going to be the same. Or you can say equal. Or it is the same. Then compare the charge. But this one is going to, because it is 0, -1, this is going to be Z plus 1. So it means Q has the charge of R, because the proton number Z gives us the charge. So it means the charge of R is going to be greater than the charge of Q by 1. So we can say charge of R is greater than charge of Q. The charge of R is greater than the charge of Q. Or you could say the charge of Q is less than the charge of R. As simple as that. Well, I think that marks the end of paper 2. I don't think there's any other question here. That marks the end of paper 2. Until next time, bye-bye.